think I put up a nice unreadable view graph about energy cost per ton of different materials. Okay. If you're trying to select materials, there's lots of different bases to select materials. And in fact, it depends on what the application is. But for structural materials, I showed you this graph that's showing that the more you use, the less expensive the material becomes over the long run. And in fact, I showed you the slope was a little bit different than the ISO market concentration. And the prediction is over the long run, if you can drop the cost of the structural material by a factor of 2, you should quadruple its use. So you actually double the market size, okay, in terms of structural materials. Then I went all the way from diamonds back to gravel. However, some things have sort of an inherent barrier, and that is the energy content. It turns out aluminum oxide, Al2O3, is a very, very stable bond, and we're only about 50% efficient, if I remember correctly, at breaking that bond energetically now, commercially, but even so, it takes 300 gigajoules per ton, and that means that out of let's say a $1 per pound price of aluminum. Now, different aluminum alloys can go from basic aluminum ingot at 60 or 70 cents a pound, depending on whether the world market, okay, or to $2 a pound or $4,000 a ton for some heat-treated aluminum plate that might go into an aircraft wing or something like that. Now, in that 60 to 70 cents a pound for the base aluminum, you may have 40 cents worth of energy. So how low can it go? Unless you can get the energy cost down. Now, right now, most of the energy for producing aluminum comes from hydroelectric power. And the reason for that is hydroelectric power, if you happen to have big rivers and you want to invest in a great big hydroelectric plant, hydroelectric power is the cheapest electrical energy in the world. You can get it down on the order of 1 cent per kilowatt hour. Now you're paying 8 cents a kilowatt hour or 10 cents a kilowatt hour here in New England, but if you're going commercial and you're buying lots of it, in some parts of the world it may be ½ cent per kilowatt hour. Most of the cost is the capital cost of building the hydroelectric plant to begin with. Once you pay for that, it's almost a sunk cost, and the water's going to keep flowing, and you've already got the plant. So the problem in the aluminum business is when everything tanks out, when the economy tanks out, whether you're Venezuela, which has lots of aluminum production because they have lots of waterfalls and hydroelectric plants, or whether you're Brazil, down in southern Brazil, or whether you're Canada up at James Bay, where they built these huge electrical generating plants, or whether you're the former Soviet Union, you're going to sell aluminum at whatever you can get it for, because otherwise the water's just running to the ocean and you're getting nothing for it. You got to pay the interest on your plant. And it's the same type of thing as overcapacity in the semiconductor business or the steel business. The problem, some people call aluminum canned electricity, because what you do when you make aluminum with a hydroelectric plant is you make that energy easily transportable. The problem, you can bring James Bay power down to New England, but you lose about 50% in the transmission. And so therefore what you might be generating up there for 1.8 cents or something costs you 3.6, and you can sell it for 8 cents and make a tiny profit, even with all the middle people along the way. However, James Bay just happens to be lucky to be that close to a megalopolis of New York and New England and whatnot. Venezuela is a little harder. You can ship the electricity to Caracas, but they can't eat all the energy. That, Caracas could make it look like noontime with lights if they wanted to, right? In terms of all the energy they got in terms of hydroelectric power. So instead, rather than just making it so everybody in Caracas thinks it's summertime at the North Pole at night, they basically make aluminum and sell it on the world market. Okay, when there's a shortage of aluminum, they make lots of money. When there's not a shortage of aluminum, they don't make as much money. but hopefully they cover the interest payments on their capital investment. And you can see plastics inherently, the energy content of plastics is mostly because that you can alternatively burn them as fuel, as hydrocarbons, rather than using it as plastic. But you get down here and you see that if you were to plot all that on that other type of curve I showed you, it wouldn't be perfect, but there is definitely a correlation with the cost of the material and the energy content.
Why was copper rising?
Copper is rising because there are no really high-grade copper deposits in the world. Somewhere in Zaire, there's a copper mine that has 6% copper. That's fantastic. I mean, we used to have small deposits of copper in different parts of the world. But the real problem is we are now mining in this country. I think the Kennecott mine. What's the Kennecott mine out there in Salt Lake, Chris? Big, deep mine?
Yeah,
Kennecott Copper. Yeah. What's the name of the mine? Anyway, it's Kennecott Copper.
Yeah.
That's it.
Bonneville.
Is it Bonneville? It's the world's deepest mine. I mean, it goes down about 1.5 miles. It's just kind of open pit mine. And they've been mining it for years. It's a 0.5% copper. And so you got a lot of dross to get rid of in order to get the copper. So the problem is we don't have good high concentration of copper. There is a rumor, actually probably more than a rumor now, somewhere in the middle of Australia they found a mountain full of copper that has very high grade ore. And part of this is that came out of a book that was written in the mid-80s. It's just like oil exploration. People always say, oh, we're going to run out of oil in 20 years. The reason we're going to run out of oil in 20 years is no one drills for oil when you've got 20 years worth of proven reserves. We actually will run out of oil, or all the projections now is around 2050. But the reason you don't drill when you've got more than 20 years worth of reserves is the cost of money. $1 today, 20 years from now, is only worth 5 cents. So why are you going to spend $1 finding something that you can only sell for 5 cents, in investment dollars 20 years from now? So basically, for the last 80 years, we've had a 20-year supply of oil. And that will continue for the next 40 to 60 years. Somewhere in there, we're going to get to the point where it's going to go up. Now, it turns out, well, that's kind of assuming that a $30 a barrel type of price. When it actually gets to $40 a barrel, we're going to have plenty of hydrocarbons, but it's not going to be light oils. It turns out the Athabasca tar sands in upper Alberta has more oil content. It's tar sands. I mean, they mine it with shovels. It's got all kinds of sands in it. They mine it, and they've now got the price on the best stuff down to about $20 a barrel, and so they're making money right now. But when oil goes to $40 a barrel, which it will over the next 40, 50 years, there is more tar sands than all of Saudi Arabia's oil in Canada. And if you want, the Orinoco River Valley, and Venezuela's got all this light oil, right? But the Orinoco River Basin has heavy oil deposits of 1 trillion tons, or 1 trillion barrels. I don't remember if barrels or tons. Doesn't really matter, okay? Prudhoe Bay is 16 billion barrels. Well, that kind of pales beside 1 trillion tons of heavy oil in the Orinoco Valley Basin, okay? There are hydrocarbon deposits, and the gas available in the world is about double all the oil, the light oil we've been burning for the last 100 years. The problem with gas is the same thing with hydroelectric power. It's expensive to transport. So if you can figure out how to liquefy gas, you've got light oils, high quality light oil, for another 100 years. So, but then there's the problem of global warming and greenhouse gases and everything else. But it's not as if there's a shortage of hydrocarbons in the world. The problem is the price. In all these projections, the light oils, at the rate we're using them, somewhere around 2050. Some people say 2030, some people say 2060. Somewhere mid-century, we're going to run out of the easily recoverable light oils. And easily recoverable means like $20 a barrel. But if you go to $30 a barrel, or you go to $40 a barrel, all of a sudden heavy oils or gas or other things become economical. I can liquefy gas at $40 a barrel, but who's going to go out, or even at $30 a barrel, who's going to go invest $10 billion in a gas liquefaction plant, knowing that 5 years from now it could drop down to $10 a barrel again? You'll lose your shirt. You have to get to the point. Right now, the bogey is about $17 a barrel. The long-term average price of oil over the last 10 to 15 years has been $17 a barrel. No one's going to go invest in a plant over the next 20 years. It's billions of dollars or tens of billions of dollars. No one would go invest unless they can do it for $17 a barrel, because that's the historical price over the last 10 to 15 years. However, that price is going to creep up, and all of a sudden other things are going to become economical. Okay? So it's amazing how, I wish that some media people or some politicians would go take an economics course. This is not rocket science, okay? But they don't. So. Well, actually, I didn't know this is I like your questions. The students were talking this morning about, I can't remember what got us off on this digression, but if you read the paper, Japan has got a terrible economy for the last 10 years, right? Now, I spent a year with the Office of Naval Research in Tokyo in the mid-'80s, and I came back and said, and that was when the Japanese economy was just glowing, you know, they were wiping out everybody. And I said, they got a fundamental structural problem. And I knew that their economy was going to turn bad. I didn't know when. If I could predict when, I could be a rich man. But, you know, that's the key, is knowing when. But the fundamental problem in Japan is the Japanese culture considers farming to be the noble profession. And in Japan, 30% of the workforce is in farming. In the United States, if I went back to 1810, something like 90 to 95% of the workforce was in farming. And in order to survive, you just had to have almost everybody growing food. Today in the United States, it's less than 3% of the workforce is in farming. And we're exporting food, right? Well, it turns out, because of the Green Revolution in the 50s and 60s, people were predicting in the 50s that the world was going to starve to death within 10 years. But because of the Green Revolution, they're getting like 6 times the rice crop per acre in the world, such that China, you know, in the 70s, China got to the point where it can feed itself. And India can feed itself. There's very few countries that can't feed themselves now. The problem we have, there's still people starving in the world. About 1 billion people a year go to bed hungry every night. That's a distribution problem. That's not a resource problem. That's a distribution corruption problem in the world. The problem the Japanese have is you're not allowed to import rice into Japan. It's illegal. Japanese agree that California rice tastes much better than Japanese rice. Japanese rice sells for 7 to 10 times the world market price. They basically have fixed barriers to keep 30% of the workforce in farming. They have these little plots. Some of them aren't even bigger in this room, okay? And people have to make a living on a little plot. And so they have to have a very high rice price. So what do you expect your economy to do when you're going to have 30% of your people in a non-productive occupation? I mean, the Japanese, if they wanted to fix their economy, all they have to do is open up the market to rice. Of course, politically it's unacceptable, which is great because we no longer have to worry about the Japanese owning America. But, you know, that's one problem. Now, so we'll turn this to the economics course. What's the fundamental problem in Europe? France is the perfect example. In Europe, the fundamental problem is you can't fire anybody. You hire them for life. You got them for 30, 40 years. You try to lay someone off in France, forget it. It will cost you twice as much as if you just keep them on the rolls sitting at a desk for the next 20 years. So as a result, if you're a business person in France, you're never going to build a new plant where you have to hire new people or something like that because it's a 30-year liability. And you can't afford to invest more than 20 years into the future. So the Europeans, in their social wisdom of making sure everyone's employed, have created a system that is going to guarantee unemployment because the business people have no incentive to hire anybody, except in the most dire of circumstances, okay? So, I think it's great. I mean, I actually am a free market person. If the Europeans want to compete with us on the basis of you can't fire anybody, and the Japanese want to compete with us on the fact 30% of the workforce is going to be growing rice at 10 times the world market price, great. Okay, it's good for American business. Which actually brings up another question. How smart are American businessmen? They tell you they're brilliant, right? But when you've got competition like that, how brilliant do you have to be? Okay. You're hearing my sentence. Okay. Aside from the fact of energy costs and things, when we're talking structural materials, the most important properties are strength and toughness. Actually, strength, toughness, and cost, but I've already been talking about cost. Let's talk about toughness. This is one of the Ashby plots for fracture toughness versus strength. And you have various types of, this is yield before fracture, guidelines for safe design, the different types of slopes on here. The slopes are the fracture toughness divided by the fracture strength squared, or actually the fracture toughness squared divided by the fracture strength squared. That comes out of fracture mechanics calculations. We'll talk about fracture mechanics later, but not as in depth as that. That's not as terrible. Slopes. And you want to have both high fracture toughness and high strength, and so you want to be out here as far as you can. Okay? And actually, I guess you want to be up here as far as you can. Somewhere out here. So, what is the furthest out? It just so happens that it's steel. Steel is tougher than any other material that we have. Copper alloys are pretty good. These are the engineering alloys. He calls them engineering alloys. These are graphite fiber reinforced plastics, carbon fiber reinforced plastics, which is that space shuttle or the X-33 and stuff. So if you want to pay $10,000 a pound, you can use this material. It competes pretty well with metals and it's lighter. We don't have density here. I do have the plot of fracture toughness versus density. And he has a plot of fracture toughness versus cost. But I've already got 4 parameters now. I've got cost, fracture toughness, strength, and density, all trying to make some sort of structure. I can't plot them all on one plot, but I can plot them different ways. Just fracture toughness versus strength. The steels are up here, nickel alloys, copper alloys. Here are your ceramics down here. These are orders of magnitude lower. Okay, I've got common rocks down here. I've got plastics down here. These things, these other materials, yeah, if I want to make some children's toy for Fisher-Price, yeah, I can use plastics. If I want to make some liner for the inside of an automobile, I can use plastics. But as the basic structural material that's going to absorb energy in a crash for that automobile, it's steel. Cheap. Now, aluminum can absorb energy and it can be lighter weight, but it doesn't have the cost advantage. If I divide this by density, steel still comes out on top unless I'm moving very fast. Lightweight is only important if I'm moving. And the corollary to that, the faster I move, the more important low density is. If I'm building a bridge, it doesn't move very fast, hopefully. That means I can make it out of concrete. I can make it out of steel. I can make it out of lead if it was a better material. I don't care about the weight. However, if I'm building something that has to be high performance, I'm going to sell someone a $50,000 Audi with a 2.6 liter engine or something, whatever the engine size is. And I want, that person for their extra $30,000 they're paying for that car, they want some performance. I'm going to make it out of a lighter weight material because then, that energy will be able to move less weight faster. Won't be able to crush and absorb energy in a crash as well, but that's their problem when they have a crash. And hopefully we can design around that with different types of structures. Steel is still the cheapest for building automobiles. And the high volume cars, both for welding reasons and cost reasons, are going to be made out of steel for many years to come. not to say we're not going to see more and more aluminum and more plastics in certain areas, but it's not the fundamental structural area. That's true for lots of things. Now, if I want to go and improve the performance of a car, where should I put the weight? Where does it move fastest on a car? The wheels. And more, you're seeing cast aluminum wheels or forged aluminum wheels on automobiles. Why? Because the wheels are moving faster than the rest of that car. And that's where the lightweight pays off the most. We're going to get to friction welding, and we'll talk about linear friction welding, where people want to build a turbine disc for the Air Force's next fighter. And they want to go from a flange joint for these types of turbine blades I showed, which is very heavy, to a welded joint. They can take 20 pounds out of every disc. That's 200 pounds out of every engine, which is 2,000 pounds out of every airframe. Why? Because the disc goes at very 18,000 RPM, or 1,800 or 10,000 RPM, whatever. Lightweight is important when you go fast. Lightweight is not important when you're not going fast. Cost becomes the primary thing. Now, so far as toughness, almost time to quit here, but let me show you a plot of what's called a ratio analysis diagram. This type of diagram was developed at the Naval Research Lab in the 1950s by a guy named Bellini, who later became, after he retired from the Navy, a professor, visiting professor here at MIT. He retired at Cape Cod. But it plots fracture toughness versus yield strength. These are the two important things, but in a slightly different way than not on a log scale. And steel tends to form a band like this, titanium here, aluminum here, composites here, and ceramics are down here. Turns out this is the elastic plane strain region. This is called brittle materials. You don't want to design down here. You hit it very hard, you have a defect in it, it shatters. Not a good structure. General plastic yielding, only the nuclear sub people can afford materials like this. As Professor Clue used to say, they'd much rather slowly squeeze to death rather than drown. Where you usually design is here in the middle. You can get a certain toughness and you can get a certain strength. And this is elastic plastic mixed mode type of fracture mechanics. Steel is still better than titanium. Actually, steel, titanium, and aluminum, all in this band down here, can be used for a structure, but steel's got the greatest toughness. It's going to absorb the most energy. So if you talk about energy absorption as another parameter in here, which is related to the fracture toughness, steel has yet another advantage. But it's heavy, and you can't always afford that extra weight. Okay, I'll see you.